tab, where we are looking at interview questions one by one, have a little deep dive to understand the details of the question being asked, and then come up with an informed solution for that question, and discuss on the solution. And today it's going to be another question from machine learning, specifically deep learning. What is the significance of residual networks is a commonly asked question. And in order to come up with an informed solution, we should have a look at what are residual networks in the first place. And the authors of this blog post, the author rather, Ragunan Depu, defines it by motivating it from a standpoint where you have a deep neural network, but the problem is that at certain points you have vanishing gradients, and the gradient signal that comes back goes to zero at certain points, making the learning rate, the learning following the gradient descent relatively slow. And when we, as you say here, when we backprop from the final layer back to the first layer, we are multiplying by the weight matrix at each step. If the gradients are small, he says, the gradient can decrease exponentially quickly to zero. And that happens, for example, in standard networks like VGG16. So the thing is, it happens because deeper networks are able to start converging. Degradation problem has been exposed. With the network depth increasing, accuracy gets saturated and then degrades rapidly. Using deeper networks is degrading the performance of the model. So the way to fix it is to introduce like some sort of skip block or skip layer, where you take the output at a first layer or even at the very entrance layer and just like propagate it alongside all the other layers of the deep neural network up until the point or up until the layer where you want to feed it in as well. And it's gonna be like illustrated somewhere like here. You're skipping basically this this layer with an activation function, and then you have another layer, and then you're just adding your original input with a plus sign to it, and then you invoke your activation function. So, and they found that such an additional layer will not hurt the model's performance when you skip over a certain layer. If the additional layer was useful, even with the presence of irregularization, the weights or kernels of the layers will be non-zero and the model performance could increase slightly. So adding those new layers is guaranteed that the performance of the model does not decrease, but in fact actually increases slightly. So if you stack those layers on top of each other, you can actually have a very different deep neural network. They call it a ResNet. A ResNet blocks makes it easy for one of the blocks to learn an identity function. So you can stack them with little risk of harming your training set's performance. And there's like basically two main types that you can imagine. One is really just like taking an input, the beginning or the second step of your neural network, and then just adding it to whatever output has come forward from your network at that point, and then just add it to it and then perform your activation function on top of it. The second approach would be to manipulate your data at that point with another convolution or batch norm, and then add it together with whatever output your neural network has performed up until that point, and then perform the activation function again. So it's either identity, just pass it through as it is, or perform a convolutional block on top of it. And findings from research show that it's successful. So it won first place in certain classification problems. And they could show that VGG16, a plane network with ResNet 101, observed a relative improvement of a quarter of like 28%. And this way you could effectively train very, very deep networks with 100s and 1000 layers. And they summarize and say, okay, very deep neural networks are not practical to implement because they're hard to train due to those vanishing gradients. Those skip connections from resonance, where you just like pass through with an identity or pass through with a convolutional block, help addressing exactly this problem with a vanishing gradient. They also make it easy for a ResNet block to learn an identity function. And we found those two blocks, identity and convolutional block. And very deep residual networks can be built by stacking those blocks together. And with that in mind, let's go back to the question and see how we can concisely answer it. The concise answer for the question would be the main thing that a residual connection did was allow for direct feature access from previous layers. This makes information propagation throughout the network much easier. One very interesting paper about this shows how using local skip connections gives the network a type of ensemble multipath structure, giving features multiple paths to propagate throughout the network. So like since we have these skip layers, a feature can either go through the long path or can go through that path where you have an identity or a convolutional block before you add it back in with the network at a later stage. And that's basically like a concise way to answer exactly the question of what's the significance of residual networks? Why would we bother to motivate the use of a residual network exactly in those cases when you have like very, very deep neural networks and you want to like propagate your original signal or your original values through the network through multiple paths.